By 2029, federal rules will push over half of new electric storage water heaters in the US onto heat pump technology, up from just 3% today. That's supposed to be the fix, the appliance that finally stops wasting your money every month. However, almost nobody buying one realizes what's actually humming inside it: a compressor and a tank of refrigerant gas running the same century-old cycle as your fridge. Chinese Academy of Sciences researchers already built a version with none of that. No compressor, no refrigerant. Driven by heat itself, moving warmth with nothing but sound. Water heating isn't a minor line item on your utility bill. The Department of Energy puts it at roughly 13% of a typical home's total energy use, and Energy Star notes that a home's water heater burns through more energy on its own than the refrigerator, washer, dryer, and dishwasher combined. It's the second biggest single energy draw in most houses, right behind heating and cooling the building itself. That's exactly why regulators picked this appliance to force a technology shift on, and why the machine sitting quietly in your basement or closet is about to become one of the most contested pieces of engineering in your home. Here's what that mandate is actually pushing into your basement. A heat pump water heater doesn't create heat the way an electric resistance tank does with a glowing coil. It pulls warmth out of the surrounding air and dumps it into your water, the exact same trick your refrigerator uses to keep food cold, just running in reverse. Inside the unit sits a small compressor, squeezing refrigerant gas until it gets hot, then letting it expand until it gets cold again. That compressor is why heat pump water heaters use a fraction of the electricity a resistance tank does. It's also a moving part that wears down, a seal that can fail, and a refrigerant charge that can leak out over the appliance's life. The Department of Energy says switching a typical home from resistance to heat pump technology saves around $1,100 over the water heater's lifetime. And across every household the new rule eventually reaches, the department's own estimate puts the national number at $7.6 billion a year in savings once it's fully in effect. That's the pitch for heat pump technology in general. It says nothing about whether a compressor is the best way to get there or just the only way anyone's built at scale so far, until a lab on the other side of the planet started asking the same question the regulators never did. In 2023, a team led by the Chinese Academy of Sciences, working with Germany's Karlsruhe Institute of Technology and China's Tsinghua and Southeast universities, published a heat pump built to answer that exact question. It has no moving parts. None. Instead of a piston squeezing gas, the system runs a loop of 3 connected parts: an engine unit, a heat pump unit, and a resonator tube full of pressurized gas. That international mix matters. It means the physics behind the prototype was checked by peer reviewers across 2 continents, not just cleared internally by one lab eager to publish good news. Heat goes in one end and comes out as sound, an intense, engineered wave bouncing back and forth inside a sealed tube. Inside a normal speaker, sound is a byproduct, a little bit of air pushed around as a side effect of pumping electricity through a coil. Here, sound is the entire machine. Tune the resonator tube to the right length and pressure, and a loud enough standing wave inside it behaves exactly like a piston slamming up and down thousands of times a second, without an actual piston touching anything. Gas near a pressure peak genuinely heats up. Gas near a pressure trough genuinely cools down. Put heat exchangers at the right spots along that tube, and you're pumping real thermal energy from one end to the other. The same outcome a compressor delivers, produced by acoustics instead of mechanics. In testing, the prototype hit a heating capacity of 5.7 kilowatts and a coefficient of performance of 1.40 at its nominal setting, and in the 50 to 70 degrees Celsius range your hot water tank actually runs in. It delivered between 1 and 11 kilowatts of heat. No compressor, no refrigerant gas, just heat, converted into sound, converted back into heat. There's one more detail that makes this stranger than a normal heat pump swap. A standard heat pump water heater, compressor and all, still needs mains electricity to run that compressor around the clock. The thermoacoustic version doesn't. It's heat driven. The temperature difference between the warm source and the cooler sink is what generates the acoustic power in the first place, the same way a steam engine turns a temperature difference into motion instead of consuming it as fuel. Feed it waste heat or a solar collector, and in theory it produces hot water while pulling almost nothing from the grid. That's a second problem solved inside the same tube that solved the first one. If a piece of 1800s engineering hiding in your basement can get quietly replaced by sound waves, it's worth knowing what else is on its way out. Subscribe if you want to catch the next one before it hits the mainstream press, And this isn't a one-off lab curiosity that got published and forgotten. The same institute, the Technical Institute of Physics and Chemistry within the Chinese Academy of Sciences, kept pushing the same sound-driven idea further. Led by physicist Luo Erkong, the team built a second, much larger prototype aimed at heavy industry instead of homes. And in December 2025, it made headlines for pumping heat past 200 degrees Celsius, peaking at 270 degrees from a source of just 145, with a coefficient of performance of 1.68, published in the peer-reviewed journal Applied Physics Letters. That industrial version isn't the same machine as the domestic prototype. It's built for petrochemical plants and metal smelters, not your bathroom. But it proves the underlying trick. Heat converted to sound and back with no moving parts scales upward. Luo's team has already said publicly it wants to push the same acoustic trick into the 500 to 800 degrees Celsius range next, aiming at industries that currently have no electric alternative to burning fuel at all. The team that could delete the compressor from a water heater is the same team now trying to delete it from a steel furnace. Western manufacturers are racing to keep up with the heat pump wave just with the old architecture. In August 2026, A.O. Smith, one of the oldest water heater brands in America, launched its own heat pump water heater built around CO2 refrigerant, rated to keep working reliably in outdoor temperatures down to negative 31.7 degrees Celsius. That's a genuine engineering upgrade, and not a small one. It's also still a machine with a compressor and a refrigerant charge inside it, the same basic architecture the industry has used for decades. A lab in Beijing already published the version that skips both. None of this means your next water heater is getting a sound-powered core anytime soon. A coefficient of performance of 1 is modest. Current electric heat pump water heaters already on store shelves often clear 3 to 4, so the domestic thermoacoustic prototype still has real efficiency ground to make up before it can outcompete the compressor it's trying to replace. The 2023 paper was a proof of concept, tested in a lab, not a product sitting in a warehouse waiting for a supply chain, and nothing about a commercial timeline is guaranteed. Thermoacoustic systems have also historically struggled with manufacturing costs relative to a mass-produced compressor, and nothing in the 2023 paper claims that problem is solved. Cost, manufacturing at scale, and long-term durability outside controlled lab conditions are all still open questions the researchers themselves haven't fully answered yet. But here's the part worth sitting with. The compressor at the center of nearly every heating and cooling appliance built since the 1800s was treated as a fixed piece of physics, something you engineer around, not something you delete. A Chinese state research institute has now proven, twice, in 2 different temperature ranges, that deleting it isn't science fiction. It's a resonator tube, a loop of pressurized gas, and heat doing a job electricity used to do alone. If a version of this ever reaches store shelves, replacing the compressor stops being just a materials science story and starts being a repair bill story. Fewer seals to fail, less refrigerant to buy, one less part an technician has to bleed and recharge on every service call. Somewhere between a quiet university lab in Beijing and a factory floor in Foshan, that gap tends to close fast. The water heater humming in your basement right now still has a compressor in it. It might be one of the last generations that does.